Please welcome me.
Okay, thank you. Can everybody hear me well at the back? Yeah? Okay. So I'd like to start by thanking the organizers for the invitation and putting together this wonderful school. It's a real pleasure to be here, have the chance to speak at the school. So I'm not going to talk about scattering amplitudes per se, but something closely related called cosmological correlators. Okay, so these are the fundamental observables that we care about in cosmology. So in this series of lectures, I would like to tell you some modern perspective on this object in cosmology, and see how various techniques and tools that we have developed in particle physics in flat space can also shed light on the structure of the early universe using these objects. Okay, so let me begin by stating the goal of this lecture. Okay, so this is to understand the physics of the primordial universe. So by primordial universe, I mean the earliest history of the earliest phase of the history of the universe that we don't have direct access to observationally, but nevertheless whose imprints are accessible all over the universe today. So the question we want to ask is, what are these fingerprints of this early universe physics to late time observations, and what physical processes actually produce them? Okay. So normally in most of the areas of science, other science, the way we approach this kind of questions, fundamental questions in science, is that we run experiments many times and study the outcomes of that experiment to learn about the physics or the science. So here in cosmology, we actually seems to have a limitation that we face a challenge, namely that we can't really rerun the birth of a universe. Okay, we can't really recreate the condition of this super early period of the universe in a lab. Okay, so the question is, what do we do? Well, what we do is that we rely on this key idea, which is that the early universe already ran an experiment for us. Okay, and we can study the outcomes of this experiment. Okay, and also crucially, the universe, the observable size of the universe is huge. So that means that we can effectively have access to many independent, statistically independent regions of the universe in the different patches of the sky. So we are effectively getting access to a huge ensemble of repeated experiments from the early universe. Okay, so the result of this experiment are the patterns that we can see in the distribution of matter in the universe, for example. And we will refer to those objects as cosmological correlators. Okay. So the patterns that we see in the distribution of matter in the universe are not going to be completely random, but they will instead encode the physics that were generated in the early phase of the universe. Okay, so what do we exactly mean by this correlator? So let's try to be a little bit more quantitative. Okay. So to get an idea, imagine you divide the sky into a grid, and then what we can do is to start counting the number of galaxies in each patch of the sky. And when we do that, we will find that the number of galaxies will be different in different patches of the sky. Say, so one patch will have more galaxies compared to the other patches. Okay, so they're not going to be completely uniform, but there will be some fluctuations, but this fluctuation will not be totally random. Okay, so what we can do is to say the specific quantity that we are interested in cosmology or something called the density perturbation. Okay, so instead of counting the number of galaxies, the quantity that we can also measure in the universe is something called the density perturbation. So this delta rho is the density perturbation at some location x away from the average density of the universe. Okay, and this is some dimensionless number. Okay, so this quantity density perturbation refers to a fractional deviation from the mean of the density at a local density at a given point position x. Okay. But we are not necessarily also interested in the density of the matter at some specific location, but we are instead interested in statistical patterns. Okay? So what we can do is to take this density perturbation at some position x, and then multiply by the density perturbation at some different position x2, say, and then we take this product and then average over the entire sky. So this is what we mean by taking the correlation function. Okay, so this in particular is a 2-point correlation function of density perturbations. Okay. So what this physically mean is that if you have some density perturbation or the number of galaxies in a given patch that is larger than the average, then what is the probability of observing another nearby patch having also a number of galaxies that is larger than the average? So that's the information contained in this kind of 2-point function. Now, turns out that our universe is statistically very homogeneous and isotropic. Okay, so that means that the sky looks roughly the same everywhere. Okay, so this 2-point function, even though it depends on 2 different positions, is really a function of just the distance between these 2 points. Okay, so this 2-point correlation in cosmology is just going to be dependent on the difference between these 2 positions. Okay, so it's some function of the distance between these 2 vectors, and furthermore, because the universe looks almost the same in every direction, so the universe is statistically isotropic. So this function actually only depends on the magnitude of the difference between these 2 vectors. Okay? And because of this spatial translation invariance that we have in cosmology, it is often very useful to go to Fourier space to talk about this 2-point function. And when we go to Fourier space, it's going to be some function of just the magnitude of the wave vector. Okay, so this function, when we go to Fourier space, is what we call the power spectrum. And this power spectrum is one of the main observation quantities that we care about in cosmology. And in the series of these lectures, we'll be also looking at higher point correlators of this sort as well. Okay. So here I just talked about the correlation of density perturbation in the universe, but we can also talk about the correlation of temperature fluctuations in the universe. So we can similarly divide the sky into a grid and then try to measure the temperature across different patches. Then some patches will be hotter and some patches will be slightly colder than the average. And there will be some correlation between these cold and hot spots on the sky as a function of the angular position of the sky. Okay. So these are the main objectives we want to study, and the type of questions that we want to learn about them are what do these correlators actually look like? And also what rules do they follow? Okay, so these will be the guiding questions that we will consider throughout these lectures. So the outline of the lecture is the following. Okay, so here's the plan. So in the beginning, so I assume that most of the people in the audience are not working cosmology, so I'll try to be pedagogical in building this up. Okay, so the first part of the lecture will be about perturbations that exist in the primordial universe that we refer to as primordial fluctuations. In the second lecture, in tomorrow's lecture, we will be looking at the formalism for computing these correlation functions in the early universe using the object so-called wave function of the universe. Okay, and in the third and the fourth lecture, we'll be asking a slightly different question. Okay, so instead of trying to compute these correlation functions using some brute-force direct method, we'll ask a slightly different question, namely, can we avoid this type of direct computations using Lagrangians and Feynman diagrams and so on, but instead whether we can directly determine or bootstrap these final answers for these correlators using principles like unitarity, symmetry, and locality, and so on, like we do in scattering amplitudes. Okay, so I'll be talking about an approach called the cosmological bootstrap. And finally, I'll be talking about a method that has proven very powerful in organizing the structure of these correlation functions using the method of differential equations. Okay. All right. So, any questions about this plan so far? Okay, so to illustrate this idea a little bit better, let me try to draw a picture that illustrates this idea about using connecting current observation of the universe to the physics of the very early universe. Okay, so this is the timeline, and we are here today. And around us, we observe the large-scale structure of the universe consists of many different structures like galaxies, dark matter, clusters of galaxies, and so on. Okay, and as I said, we can measure the two correlation function of density perturbations in the large-scale structure. Okay, so this is large-scale structure, and then we can try to measure, say, two-point correlation function between different positions in the sky. And this quantity has been very accurately measured in observations. So if we plot this delta rho over rho two-point correlator as a function of the wave number k in Fourier space, so this quantity has been very accurately measured. It has roughly a shape of this form. Okay. So from the shape of this power spectrum, we can infer a lot of information about both the evolution history of the universe as well as the initial conditions of the universe. Okay, so for example, this type of oscillations that exist in the density power spectrum is something called the baryon acoustic oscillations that captures a very clean information about the early universe. Okay, and the overall shape of this power spectrum tells us about how this structure, nonlinear structure, have evolved throughout the history of the universe. Now, we can go slightly further back in time. And when we do that, what we'll see is that there, even though there are no galaxies anymore, we can see the cosmic micro background, the CMB, that basically gives us a snapshot of the universe about 380,000 years after the Big Bang. So 380,000 years after the Big Bang, the CMB was released. And again, we can measure the two-point correlation of the temperature fluctuation that exists in the CMB, and this too has been very accurately measured. Okay, so if we plot the two-point function of the temperature fluctuation in the CMB, so delta T divided by T bar, where T stands for temperature as a function of the angular multiple L, then this has the famous acoustic peaks that looks like this. Okay, and the shape of these acoustic peaks and the shape of this power spectrum tells us a lot of information about the composition of the universe involving dark matter, dark energy, the curvature of the universe, and the size of the fluctuations and so on. Okay, now so far I've talked about these late time observables that we can actually see in the sky, but these fluctuations must have come from somewhere. Okay, the fluctuation that existed even before the CMB was released. So if we go all the way to the beginning, then we reach something called the reheating surface. Okay, so basically, before the CMB was released, the universe consisted of a thermal equilibrium radiation, okay, of standard model radiations. And if you go all the way to the beginning, we'll find that the fluctuations are encoded in a spatial surface called the reheating surface. Okay, and basically, this is the surface. You can think of this surface as encoding the initial condition for all the structures that form in the late universe. Okay, so there exists some fluctuation that exists in this initial surface, and this surface is also you can think of the beginning of the hot Big Bang. Okay, so by hot Big Bang, we don't necessarily mean the singularity when the universe was born, but this is the period, this is the moment when the universe was in thermal equilibrium with all the standard model radiation at super early times. So we have also measured very accurately the type of power spectrum that exists in this early reheating surface. And as I'll tell you in a bit, these fluctuations that exist, we usually study them using a quantity called zeta, called a curvature perturbation. And if we plot this zeta 2-point function in Fourier space, normalized by k cubed, then we see that this spectrum looks almost flat. Okay, so this is an almost flat spectrum with a small tilt. Okay, so this is what we have observed so far about this initial condition. And it seems like this has a very special feature. So this is given by, first of all, given by a nearly flat spectrum like this. And also, turns out that this correlation exists on extremely long scales, larger than the size of the horizon time of reheating. Okay, so the question we want to ask is what mechanism was able to produce this set up this initial condition at the beginning of the hot Big Bang? So the leading idea that we have is that there was some period of rapid expansion at a nearly exponential rate that we call inflation. Okay. And the nice thing about inflation is that it gives a dynamical mechanism for setting up this initial condition, where these fluctuations really began as a tiny quantum fluctuations. And because of this rapid exponential expansion during inflation, these tiny quantum fluctuations get stretched out to macroscopic distances, setting up this initial conditions at the reheating surface. Okay. Yeah.
You said we know the last power spectrum. I mean, I kind of know that the macro spectrum for your things you said on this, but where do you get the data from, for example? Because I mean, we can't see, but half Big Bang is light, right?
Yeah. So what we do is that the physics that relates this CMB power spectrum and the initial power spectrum of zeta is mostly linear. Okay. So that means that we can basically undo this time evolution from the time of the CMB back to the initial surface. So even though we don't directly see these curvature perturbations.
So we do some mathematical backpropagation.
Yeah, so there's a relationship between zeta, curvature perturbation, and the temperature fluctuation in some linear fashion. Okay, so we can basically undo that linear evolution to extract, basically extrapolate. Yeah. You can also do that starting from the larger structure 2-point function, but as you go to more and more nonlinear scales, the physics become more complicated. So you might have to run simulations to extract the initial power spectrum and so on. But from the CMB alone is very direct extraction. Any other questions? Okay. So let me talk a little bit more detail about what these curvature fluctuations are about. So during inflation, so let me talk about the types of primordial fluctuations during inflation. So actually, there exists two types of fluctuation that exist during inflation. So one is the one that I just talked about, the zeta, called curvature perturbation. The other degrees of freedom that exist during inflation is what we denote as gamma ij, and these are gravitational waves. Okay, so these are the two degrees of freedom that are guaranteed to exist during inflation, and they basically describe the perturbation that exists in the metric. Okay, so the spatial part of the metric, Gij, in an expanding spacetime, can be written in this form. Okay, so this A of t is a so-called scale factor. Okay, so that basically tells us the rate at which the universe is expanding as a function of time. And this zeta is the curvature perturbation that is basically the local fluctuation in this scale factor. Okay, so this is a scalar quantity. And then there's the trace-based transverse part of the perturbation given by this gamma. Okay, so gamma is transverse, so its divergence vanishes and also its trace-based. Okay, and these zeta and gamma parameterize the dynamical degree of freedom that exists in the metric. Now, during inflation, this A of t is roughly going as this exponential form. So e to the ht, where h is called the Hubble parameter that is roughly constant during inflation. All right. So it turns out that these two degrees of freedom are generated quantum mechanically during inflation. Okay, so if you draw some picture. Okay, so now I've drawn this reheating surface in 2D. Okay, so this is the reheating surface. And now starting from some tiny quantum fluctuations, then because of the due to the expansion of the spacetime, the physical wavelength of this perturbation grow as a function of time. And eventually, when it reaches the reheating surface, the wavelength, physical wavelength of this perturbation is much larger than the Hubble radius that sets the size of the horizon at the reheating surface. Okay, so inflation very nicely provides a dynamical mechanism for setting up this initial condition at the reheating surface, starting from tiny quantum fluctuations. And the way this works is because of the some magical fact that zeta and gamma actually becomes constant as time goes towards the end of inflation. Okay, so that means that so zeta and gamma are space-time dependent quantities, but as t goes to the end of inflation, so as the inflation ends, these gamma and zeta becomes constant, and we say that these variables freeze out. Okay, so zeta and gamma really become just a function of positions on this reheating surface. They don't decay, but they stay constant. Okay. And because they stay constant, they basically survive after the end of inflation and set up the initial condition at the reheating surface that provides the seeds for all the structures. So in particular, zeta is a scalar perturbation that basically sources the density perturbations, and this gamma ij is a spin 2 perturbation, so they don't directly source density perturbations, but it turns out they can be detected in the polarization pattern in the CMB some specific polarization called the B mode polarization of the CMB. Okay? So if you detect some primordial CMB B mode, then it's likely that it comes from the spin-two perturbations during inflation. Okay. So now let me briefly review how these perturbations actually become generated in a simple model of inflation. Okay. And the simplest model of inflation that we know is something called a single field slow roll inflation. Okay, so let me write down the action. So this single field slow roll inflation is basically a scalar field coupled minimally with gravity. So it has an action given by this. So there's a usual Einstein-Hilbert term, and then we have a kinetic term for the scalar field minimally coupled to gravity with some potential. Okay. And this scalar field is a function of both time and position. And we can decompose this into the background evolution of the scalar field. So phi bar is just a time-dependent background of the scalar field. And then we can separate it from it the perturbations. Okay, delta phi. Okay, so this will be the classical part of the scalar field, and this is the quantum fluctuations around it. So let me talk separately the background evolution of the scalar field and its quantum fluctuations. Okay, so first let me talk about the background evolution. So from this action, we can derive the Einstein equations that govern the background evolution, which is given by 3m Planck squared, h squared is equal to 1/2 phi bar dot squared plus v of phi bar. Okay, so here dot is the time derivative. So this is the kinetic term and the potential. And then from the other Einstein equation, we also get this equation. H double dot, H dot is equal to minus 1/2 phi bar dot squared. Then we also have the equation of motion for the phi field. So this is given by the usual Klein-Gordon equation with the Hubble friction term. Of course, not all of these equations are independent. Only two of them are independent. And the first one is basically the Friedmann equation that we have in a expanding background. And here, Hubble is the rate of expansion given by the rate of change of the scale factor. It's a function of time. Okay, so with this model, what we want to achieve is to have, first of all, have an accelerated expansion. Okay, so that's basically what inflation is about. So what we want, first of all, is to impose the condition that A double dot is greater than 0, so that space-time expansion is accelerating, expanding at an accelerated rate. Okay, so let's consider this ratio A double dot over A. Now, if you take the time derivative of the Hubble, you'll find that this A double dot over A is related to Hubble by in this fashion. Okay, and you can combine them in this way. Okay, so pull out the spectra of h squared, and you get this combination in the brackets. Now I'm going to define a quantity called epsilon, and I'm going to define it as the rate of change of the Hubble in this way. With this definition, we see that this is equal to h squared times 1 minus epsilon. Okay, and we want this quantity to be greater than 0 for exponential accelerated expansion. So that implies that this epsilon must be less than 1. Okay. So let's see how we can achieve this in this simple model. Okay, so epsilon is equal to minus h dot over h squared. Now, using the second equation above, we can write this as phi bar dot squared divided by twice m prime squared h squared. Now, if we so we want this ratio to be much less than 1 to have accelerated expansion. Now, one way to achieve it is by imposing this condition that phi dot squared is much less than the potential. Okay. Now, if we do that, then from the first equation we can ignore the kinetic term, and the left-hand side is roughly becomes the potential. So this is roughly equal to the potential, and this is much less than 1 by the assumption. Okay. So this condition is called the slow roll condition because the kinetic energy of the inflaton is much smaller than the potential. Now, in order to solve various problems in the standard Hawking Big Bang cosmology, like the horizon problem and so on, we want inflation to have to occur for a sufficient amount of period. So we want this epsilon to be smaller than 1 for a sufficient amount of period. So we further define this quantity called eta, which is the rate of change of this epsilon, and we also impose that this is much less than 1. Okay. So you've probably seen this picture of the potential for inflaton. So we basically want something like this, where the inflaton sits on the top of the potential, and then it basically slowly rolls down the potential with a small kinetic energy. Okay, so that's basically extremely brief review of slow inflation at the background level. Now let's talk about perturbations. Okay, so as I mentioned, the zeta and the gamma fluctuations during inflation have the remarkable property that they become constant at late times towards the end of inflation. And that's is due to the fact that zeta and gamma behave as a massless scalar field, massless fields during inflation that basically generate a nearly scale invariant power spectrum. Okay, so let's see how that works. So if we take the the parameterization of the spatial metric that I wrote above, together with the lapse and shift in the ADM formalism, and expand the action here to second order imperturbations, what we'll find is the second order action or quadratic action for zeta and gamma. Okay, so quadratic action for zeta will look like this when you have done the exercise. Okay, so it has some overall normalization together with the standard kinetic term that looks like this. So this is for zeta, and for gamma, we have a similar looking action with a slightly different normalization. Okay, and with a similar standard kinetic term. Okay, so these are the quadratic action for zeta and gamma. And from this quadratic action, you can compute the power spectrum using standard quantization. So let me use this one. Okay, so when you have done the computation of the two-point correlation function in Fourier space, with two different momentum vectors, you will find the following. It's given by h squared divided by twice epsilon m Planck squared, 1 over twice k cubed times some delta function that imposes momentum conservation. Okay, so let me explain how these various factors come about. So this part, 1 over twice k cubed, is basically the standard power spectrum for canonically normalized scalar field. And we get this extra prefactor from the non-canonical normalization of the zeta in this action. Okay? So basically, we get h squared divided by this factor m Planck squared times epsilon. And this delta function is a result of translation invariance that imposes momentum conservation, spatial momentum conservation of these two momentum vectors. And we get similar thing for the two-point function of the spin 2 perturbation. And this is given by 8h squared divided by m Planck squared divided by twice q. Also with the momentum conserving delta function. Yeah. Yeah, so this is really if you write gamma aj, you're looking at the amplitude multiplying the polarization vector. Okay, and then you have to when you do this decomposition, you have to sum over both of the helicities. Okay, so basically this is the sum over the two helicities of this amplitude. Okay? So that's why if you compare the normalization of this action for zeta and gamma, they differ by a factor of 8 here. But here, they actually differ by a factor of 16 because you're summing over both helicities. Okay, so I forgot to mention that when you evaluate this power spectrum, you're evaluating it at a time when these fluctuations actually exit the horizon. Okay, so I mentioned that these gamma and zeta fluctuations, the size of the physical wavelength grows as the time evolves, and eventually it exits the horizon and becomes constant. Okay, so it becomes constant when these modes exit the horizon, and that's when the physical wave number, which is given by k divided by a. So this k here is the co-moving wave number, and the physical wave number, k physical, is given by k divided by a, the scale factor. And we are essentially evaluating this path spectra when the physical wavelength becomes equal to the horizon. Okay, so this is when we're evaluating at the time when this must exit the horizon. Okay, so we are really evaluating these quantities at some specific time. Okay, when k over a is equal to h. Okay. Now, if this h was actually constant, then this spectra would be exactly scale invariant. And to see this, we recall what we mean by scale invariance. Okay, so when we try to go back to, so these are path spectra in Fourier space, and when we try to go back to the two-point function in position space by doing this inverse Fourier transform, so d3k p of k. Now, if this p of k goes as 1 over k cubed with some amplitude, then these two combine so that this basically becomes an integral over logarithmic intervals of k. Okay, so if the path spectrum goes as 1 over k cubed, then we basically saying that there's an equal power at different intervals of this log k scale. Okay, so that's what we mean by scale invariant path spectrum. Now, it turns out that these two path spectra are not exactly scale invariant because these quantities h and epsilon are evaluated at some specific time when k is above the h, but h is not constant during inflation; it slowly evolves because h dot, which is given by this slow roll parameter, is not exactly 0. Okay. So that means that there's some small scale dependence coming from these two vectors. Okay? So in observations, we typically parameterize this path spectrum in this way. Okay? So we define the so-called dimensionless path spectra by first of all multiplying by this k cubed to kill this vector. And then we have this funny normalization of 2 pi squared. So this 2 pi squared is really coming from when you do the inverse Fourier transform. You have this measure factor, but when you have done the angular integration, you get an extra 4 pi upstairs that cancels with this to give this 2 pi squared. Okay, so we define the dimensionless path spectrum in this way by multiplying the zeta path spectrum with this normalization factor. And here I'm putting in the prime here to just denote the part of the path spectrum without the special momentum conserving delta function. And this we can parameterize in this way. Okay, so this dimensionless path spectrum is going to be some amplitude called AS times some small scale dependence away from some fixed length scale. Okay, and the exponent is ns minus, defined to be ns minus 1, where ns minus 1 is close to 0. Okay, now you can do the same for the gamma. Okay, with the same normalization to define the dimensionless version. And we define this as some amplitude AT with this ratio to the power NT. And it is NT, not NT minus 1 for historical reasons. Okay. And in slow roll inflation, these NS minus 1 and NT are given in terms of the slow roll parameters that I have defined before. So NS minus 1 is given by minus twice epsilon minus eta, and mt is given by minus 2 epsilon. So these are small numbers in slow roll inflation. And some of these have been very accurate measures for, so just to get some idea, this AS is roughly twice 10 to minus 9. So it's a rather small number. So this basically tells us about the rough size of these zeta fluctuations. It's given by zeta is of order 10 to minus 5. We have also very accurately measured ns minus 1, the spectral tilt, and this is given by 0.965 plus minus 0.004. Okay, and this is measured to be less than 1. Sorry, this is just ns. So this is measured to be less than 1 at about 8 sigma. So we know that this power spectrum of zeta is not exactly scale invariant by 8 sigma, which is what actually inflation gives, because inflation predicts that this ns minus 1 is not exactly 0, but is given by these small numbers. Okay. What about the tensor sector? Well, we haven't actually measured the tensor power spectrum yet, but we have some constraints. So when we talk about the size of AT, we define some ratio of these two amplitudes. Okay, we call it the tensor to scalar ratio little r. We find it to be the ratio of AT and AS. Okay, and this is given by 16 epsilon, and this is constrained to be less than 0.036. In particular, you can use this constraint to write Hubble in terms of R. Okay, so because we have measured AS and AT is given in terms of this variable R, we can write Hubble in terms of this R in this fashion. Okay, so this is 10 to the 13 GeV. So that implies that if we happen to measure R in the near future, then it would point towards a very high scale inflation, where Hubble rate during inflation is of order 10 to the 13 GeV. Okay. Okay. So there are various energy scales. So, for example, there's a Planck scale and the Hubble scale. We don't exactly know the relative size of this. The Hubble relative to M Planck, but we have an observational bound. We have some extra scale in the problem as well. And because inflation is essentially a symmetry breaking phenomenon, okay, so I told you that Hubble is not exactly constant during inflation, so that you can think of inflation as a symmetry breaking phenomenon where we're breaking time translation symmetry. So there's some symmetry breaking scale called F. Okay, so you can think of this. There exists some Goldstone boson that reflects the breaking of this symmetry. So this is often called F pi, where pi would be the Goldstone boson that captures this breaking of time translation symmetry. And we know this scale relative to the Hubble, and this is fixed to be 58 times Hubble scale. And we know this because the ratio is basically set by the amplitude of the 2-point function. The ratio between these two Planck scale and the Hubble scale is set by this tensor 2-point function, which is not measured yet. Now, on top of these three scale, there are some additional scales that could play some interesting phenomenology. as well. So for example, we so far talked about just a single scalar field driving the inflation evolution, but if you think about UV completion of inflation, then there could exist some heavy particles during inflation, as well as some light particles that could interact in some interesting way with the inflaton field. So there could be some additional mass scales that can play a role during inflation, and also the theory for these fluctuations will have some UV cutoff scale as well. So we can think of this theory that describes the perturbation as some effective theory that is UV completed by some possibly string theory and whatever at a very high scale. So there's do be some UV cutoff scale lambda, but now there are two logical possibilities whether lambda is above or below the symmetry Grange scale. Okay, and so currently we don't know how the UV completion would work during inflation. So there are a lot of information that that would be very interesting to figure out about the physics of inflation, and these information are not directly captured by this two-point function alone. Okay, so the question is, how do we actually test the physics of inflation and learn about these extra new scales in the problem? And the answer is that we have to go beyond these two-point functions and really study higher point correlators, okay, that captures nonlinear information about the theory. Okay?
Isn't the way that you presented things, it seems like H has to be less than 10 to the power 13.
Yeah, that's right. So this is an exact relation between H and R, and because R has some upper bound, so there's some upper bound on the value of H.
Are there any models which allows you to push H to the Planck scale?
No, because we have this strict observational bound on R.
But that comes from a single field model.
Oh, for different models, yes, there's a possibility because yeah, the over amplitude of the scalar fluctuation could also depend on other quantities like the speed of sound of the fluctuations, and that can yeah, but it's, so for example, if you have a speed of sound for the fluctuation, there's typically 1/CS entering here, so that can push things a little bit around. Okay, so in order to really test the physics of inflation, the idea is to go beyond the two-point function and study what's called non-Gaussianities. Which is basically another name for higher point correlation functions. Okay, so these are something called primordial non-Gaussianity. Okay, so we can imagine some process, some physical process that generates some higher point correlation between these zetas beyond two-point function. Okay. And this three-point function will be a function of three wave vectors, K1, K2, K3. Now, in Fourier space, because of spatial translation invariance, we again have this delta function that imposes momentum conservation. Okay. So that means that this function of the three-point function is really a function of that depends on this triangle configuration. So when you sum over K1, K2, K3, they have to they form this closed polygon. And this function of dependence is a function of three wave numbers. And this function just depends on the side length of this triangle because of spatial isotropy. Okay? So when I don't write the vectors above, I mean the magnitude of these momentum vectors. And this quantity is the bispectrum. Okay? Now, this non-Gaussianity is about constraining the function, the bispectrum. And this non-Gaussianity is really characterized by its size and the shape. Okay. So by size, I mean the overall amplitude for a given function, and by shape, I mean at what configuration of this triangle the shape really becomes dominant. Okay. So let me first talk about the size of non-Gaussianity. So in cosmology, we typically parameterize the size of the non-Gaussianity code using the parameter called FNL, which is defined roughly by the ratio of this 3-point function divided by a 2-point function squared. Okay. So this is so this 3-point function is of course shape dependent. Okay, so in order to get some number out of it, we evaluate this at a configuration where all the momenta are the same. Okay, so that this FNL just becomes a dimensionless number. Now, first of all, in slow roll inflation, single field slow roll inflation, there's a minimum amount of non-Gaussianity that is expected from just the pure gravitational interactions. And that amount is roughly of order ns-1, the order of the slow roll parameters. Okay, so FNL is bounded below by this number. So there's a theory prediction just from the very minimal model. There has to be some minimum level of non-Gaussianity that is of this amount, and we call this gravitational floor. Okay, so there is a minimal level of non-Gaussianity that must be present during inflation, and here we also have an upper bound from observations. Okay, so far we haven't detected any non-Gaussianity, but we have some upper bound, and this upper bound on FNL is dependent on different shapes, but it's roughly between 5 and 50. Okay, and this is from the CMB measurement by Planck. And this FNL, if you look at it, you might not get a very good idea of what this is supposed to correspond to in terms of the actual size of the couplings in the Lagrangian. So if you try to compare the size of the interaction Lagrangian with the quadratic Lagrangian in terms of the FNL, so when taking this ratio, we should really be taking this ratio with the same number of factors of zeta in the denominator and the numerator. Okay, and when we do this, this is roughly FNL times zeta, because we have one less factor of zeta in the denominator compared to this ratio. Now, I told you that zeta is of order 10 to the minus 5, just from the amplitude of the scalar power spectrum. So this is bound to be less than about 10 to the minus 4. Okay, so that really tells us that we are really in the weakly coupled regime, where the interactions are very small compared to the quadratic part. So the signal is very tiny, but it is still very important that we push this constraint further and then try to measure this FNL, because the payoff is potentially very huge. Okay, so this measurement of the 3-point function or FNL is a direct probe of the interactions and the particle content during inflation. Okay, and hopefully in the next coming decade, the beyond CMB observations involving the larger structure might be able to push this constraint optimistically by a factor of 10 for certain shapes. Okay. So I guess I have one more minute. So let me briefly mention the types of shapes we can have for this non-Gaussianity. Okay. So we can have different types of bispectrum starting from different types of interactions during inflation. So for example, we can have a simple self-interaction of the inflaton. So in terms of the delta phi, we can have interactions like delta phi time period of delta phi cubed that gives rise to this kind of contact diagram. Okay, so here this is the type of Feynman diagrams that we draw in cosmology, where this surface corresponds to the surface, the very late time surface during inflation, and then the interactions time evolve to generate this correlation at late times. Now we can have different types of three-point function arising from this kind of particle exchange as well. Okay, so this will be coupling coupled to some extra particle, say sigma, and then this type of coupling would involve some sort of a derivative coupling of the inflaton and the extra field. Okay. Now, depending on the types of interaction that we have, we are sensitive to different shapes of this bispectrum. So, for example, when we compute, say, the three-point function of the inflaton perturbations, delta phi cubed, then in the usual way of calculating things, what we will be doing is that we integrate over time the interactions of this delta phi field until we reach the end of inflation surface.
Delta phi plus or
this will be just delta phi. So this will be delta phi, delta phi, delta phi. Okay. And we are integrating over some time-dependent interactions in this time-dependent background until the end of inflation. Now, the important fact is that different types of interactions and different time integrals lead to different shapes as a function of these momentums that are defined at this late time surface. Okay. So that means that time dependence in the bulk space-time leads to shape dependence of non-Gaussianity. Okay, so in some sense, we want to understand what is the theory that describes the shape of this bispectrum and the non-Gaussianity, and use that to infer the physics that actually occurred during inflation. Okay. So let me mention one more thing before I end. Okay, so in particular, different types of interaction can lead to different shapes in the sense that if you have just a self-interaction of the inflaton field, then because this bispectrum is also evaluated when all the wave number, physical wave number, exit the horizon. Okay, so when the physical wave number is comparable to Hubble, but because this is self-interaction, so they get dominant contribution when all of the momentum are equal. Okay, so that means that for this type of contact diagram, we will get dominant contribution to the shape that looks like just an equilateral triangle. Whereas if you have this kind of exchange type of interactions, this type of interaction can be more sensitive to the more squeezed type of triangle. Okay, so by looking at the different shape dependence of this bispectrum, we can learn more about what is the different physics that generate these correlation functions. So, for example, we can plot the bispectrum as a function of the momentum ratio. Okay, so on the right, on the left diagram, when we have a contact type of interactions, this bispectrum will be dominated when the ratio of these momenta are equal. Okay, when the triangle is equilateral, so this bispectrum will roughly have a shape that looks like this, very smooth function. Now, when you have this type of interaction, what happens is that this particle will oscillate. If this is a heavy particle, this particle will oscillate in this manner, e to the IMT, the usual plane wave. Now, we have to, in order to see how that translates to the shape of the bispectrum, we have to convert this physical scale into the co-moving scale, because this is the bispectrum is defined in terms of co-moving wave numbers. Now, this, because A of t goes at e to the ht, this e to the mt behavior really goes as a to the power I times m over th. Okay, so this turns into the shape dependence of this bispectrum as this ratio to the same power, because a enters when matters when these wave numbers are comparable to the Hubble. Okay, so as a result, for that kind of exchange shapes, what we'll see is that we'll see some oscillations of this bispectrum, and the period of this oscillation will be determined by the mass of the epiparticle. So this is sort of how we can do collider physics in the cosmological context as well, by looking at this type of oscillations, which is kind of the Fourier transform of the resonances that we see in particle colliders. And then by precisely measuring this period of this oscillation, we can determine the particle content of inflation as well. Okay, so far I haven't told you about how to actually go about computing this bispectrum, but that will be the subject of tomorrow's lecture. Okay, so let me stop here.
Please ask questions.
About coupling between the gamma and the zeta in the non-Gaussian case?
Oh yeah, so here I've defined the coupling in terms of the infleton perturbation, but they are related to the zeta perturbation by some gauge choice. So effectively during inflation, we just have a single scalar degree of freedom that sources the main density perturbation, and that depends on the choice of the gauge. Yeah, so if I mention it slightly more detail, so of course we have a theory of GR, it's a diffeomorphism invariant theory, where we have to define some gauge choice. So for example, we can talk about the gauge where zeta is 0, but then we have some infleton perturbation on top of it, like this, delta phi. But then we can equivalently talk about zeta fluctuations with delta phi being 0. So they're completely equivalent formulation. But doing calculation in this gauge is slightly more complicated because GR is a constraint theory. So to really write down the interactions of a zeta variable, we have to fully solve the constraint equation of GR. Whereas if you do this calculation in this gauge, we are effectively doing some QFT calculations of a single scalar field in some fixed metric background. So it's often easier to set up the problem in this gauge first, and then we can translate to this gauge when we want to compare with the observational quantities at late times. Because
at the gel temperature.
Sorry?
At the gel temperature.
At the
Gel temperature. Temperature is 0.
Yeah, right. Yeah, because it is zeta that is actually conserved outside the horizon that can be related to the late time observables.
Any other question?
The bispectrum functional dependence you can write explicitly, right? And this triangle, is it a representation that you are writing?
So the functional dependence of the bispectrum?
Yes.
Yeah, so you can calculate this bispectrum as a function of
explicitly, right?
Explicitly for K1, K2, K3 for some given interactions. So yeah, tomorrow I'll be talking about the method of calculating this bispectrum.
I see. Okay, thank you.
Yeah, starting from some simple interactions.
Any other question? If not, let's thanks speaker again. And we will have about 21-minute break, and then we will come back at 3:30.